James Clerk Maxwell, a genius who saw the invisible. Part 1, Prologue, The Invisible Force. The special theory of relativity owes its origins to Maxwell's equations of the electromagnetic field. Albert Einstein. The 19th century was an age of visible wonders. Steam engines roared across continents. Telegraph wires stitched the world together with tiny sparks of human intention. Photography began to freeze time into images. And science, once rooted in speculation, was beginning to take the form of something more predictive, mathematical, and unified. But behind the visible world, another revolution was quietly brewing, one invisible to the eye, yet more powerful than any locomotive or empire. It was not powered by steam or steel, but by pure thought, rigorous mathematics, and a vision that reached into the fabric of the universe. This was the revolution of electromagnetism, and its prophet was a modest Scottish physicist and mathematician, James Clerk Maxwell. Maxwell was not just a scientist, he was a new kind of thinker, a boy who drew geometric shapes in the dirt with a stick, a man who, before the age of 15, wrote papers on ovals and curves that left even professors astounded. A visionary who saw that the forces of electricity and magnetism, once thought separate, were in fact unified, moving together in a grand cosmic dance. But more than that, Maxwell was a creator of worlds. With a piece of chalk and an empty blackboard, he unveiled a system of equations that could predict radio waves decades before anyone could detect them. With the flick of light and filters, he produced the first color photograph in human history, a tartan ribbon immortalized in red, green, and blue. And with a love for molecules he could never see, he gave us the statistical theory that governs the motion of every gas molecule you've ever inhaled. In the temples of science alongside Newton, Einstein, Galileo there stands Maxwell. Yet to the public he is less known, less celebrated, perhaps because the world he worked in was not visible, but mathematical, abstract, and elegant. But to physicists, Maxwell is a titan. And this is the story of how one man with a gentle soul and a mind like lightning saw the invisible, captured it in equations, and changed the fate of the modern world. Scotland, 1831. It was the 13th of June, 1831, in the rugged hills outside Edinburgh, Scotland. The moors whispered in the wind, and the sky rolled with low clouds like a sea of wool. At Glenlair House, nestled amidst farmlands and stone walls, a boy was born to John Clerk and Frances Kay. His name would be James Clerk Maxwell. The Clerk family was descended from Scottish aristocracy, known for intellect, not extravagance. His father, a lawyer turned landowner, was a gentleman who built the Glenlair estate with his own hands. His mother, Frances, was intelligent and artistic, and she oversaw young James's early education. From his earliest days, James showed an obsession with patterns not just in nature, but in ideas. At the age of 3, he persistently asked, "What's the go of that?" about everything he saw, door hinges, bird wings, clock gears. He didn't just want to know what, he wanted to know why. The young boy with the clay models, James had few playmates. The countryside was lonely, and his mother fell ill when he was very young. She tried to teach him to read and encouraged his curiosity. But before he reached age 9, she died of abdominal cancer, a loss that shaped his emotional world permanently. To cope, young Maxwell immersed himself in creation. He crafted intricate models of geometric shapes, using clay, string, and bits of wood. He studied reflections of light in bowls of water. He made sketches of ovals, ellipses, and curves, things most children couldn't even pronounce. At the age of 14, he submitted his first scientific paper to the Royal Society of Edinburgh, a brilliant piece on the geometry of ovals. Because of his age, the paper was read aloud by a tutor, but the content was all Maxwell's. It stunned the professors. The boy was no ordinary student. He was already beginning to think like a physicist. Edinburgh Academy and the Origins of Genius. At Edinburgh Academy, James was a quiet, awkward boy. His classmates mocked his accent and his strange obsessions. They called him Dafty, a cruel nickname, but Maxwell did not lash out. He retreated inward, losing himself in books, mathematics, and thought. He devoured Euclid's Elements before most had learned algebra. He was especially drawn to geometry, its perfection, its logic. His early notebooks show pages filled with constructions of spirals, ellipses, and patterns. To him, the world was made not of matter, but of forms and relationships. Later, a classmate recalled, he seemed to think in diagrams. This was Maxwell's gift. He could think in abstractions that others couldn't see. Where most people saw objects in matter, he saw fields, waves, forces, invisible structures underlying reality. But his journey was only beginning. Ahead lay Cambridge, electricity, magnets, and the most beautiful equations ever written. Ahead lay the moment when this quiet boy would become a revolutionary. And it would all begin with a question not unlike the one he asked as a toddler. Pardon. A Scottish Ganyus is born. The green hills of Scotland have long whispered songs of intellect and resilience. Among ancient castles, foggy moors, and stone cottages, many a thinker was born, but none more quietly brilliant than James Clerk Maxwell. His story did not begin in a prestigious university or a royal palace. It began in the solitude of the countryside, in a house called Glenlair, with the smell of peat fires and the sound of sheep on the hills. It began in Kirkcudbrightshire, far from the cities, where the natural world, untamed and unexplained, became his first textbook. Glenlair House, 1830 et 1839. The Clerk family had ancient roots in Scottish nobility. They belonged to the clan Clerk of Penicuik, a line that traced back to the 13th century. But nobility in name did not mean excess in wealth. James's father, John Clerk Maxwell, was a man of calm temperament, slow speech, and methodical habits. A widowed lawyer turned country gentleman, he poured his energy into farming, tinkering with drainage systems and improving the land. He added Maxwell to the family name to reflect an inheritance through marriage. His mother, Frances Kay, came from a distinguished legal family and was both intellectually and emotionally refined. It was she who taught young James the alphabet, basic arithmetic, and the Psalms by heart. She noticed his early inquisitiveness and nourished it. She would later write to a friend, "He seems very fond of geometry, and I try to explain as much as I can to keep up with him." But tragedy came early. Frances fell ill with abdominal cancer. In 1839, when James was just 8 years old, she died. Her death shattered the household's balance. Maxwell's grief was inward and lasting. His father, though devoted, was emotionally distant. From this point on, James's emotional world narrowed. He poured everything into ideas. The solitary boy and his universe of curves. After his mother's death, James was tutored at home. His first instructor, a rough countryman, treated education like discipline and showed little patience for a precocious boy who asked why more than how. When he scolded James for asking too many questions, the boy fell silent. Soon a replacement came, a more gentle and educated tutor named Mr. Nicol. Nicol recognized James's talent, especially in geometry and drawing. The boy was soon spending hours with string, paper, wire, and clay building models of curves and exploring patterns of reflection and symmetry. He was fascinated by light, mirrors, and shadows. At just 10, he built devices to measure angles of reflection using bowls of water, bits of mirror, and candlelight. He'd stare into soap bubbles and marvel at how light broke into color. The seeds of his future theories in optics were already planted. More than just knowledge, James was developing a philosophical lens, that nature was not random, but governed by hidden order. Geometry was not just abstract, it was the fingerprint of creation. Arrival at Edinburgh Academy, 1841. At the age of 10, Maxwell was enrolled at the Edinburgh Academy, a rigorous all-boys school known for its emphasis on Latin, literature, and mathematics. But the transition was hard. He had grown up in rural isolation and now found himself surrounded by louder, more socially polished city boys. His accent thick and rural, and his absent-minded ways made him an easy target. He was given the nickname Dafty. Still, ridicule never broke him. He often walked long distances from his aunt's house to the academy in deep thought, mumbling theories aloud. He dressed oddly. He read obsessively. He drew spirals and curves during recess. One classmate recalled, he had a habit of appearing to think about everything at once. But when you asked him something, he'd suddenly give you an answer that seemed to come from nowhere and yet was perfectly right. Maxwell was especially drawn to the mathematics of Euclid and to conic sections, ellipses, hyperbolas, parabolas, forms that later found their way into his scientific modeling. These weren't just figures to him, they were keys to understanding the universe. The first scientific paper, A Boy Among Men. At age 14, he astonished his professors and his father by writing a paper titled On the Description of Oval Curves and Those Having a Plurality of Foci. In this work, he used mathematical precision to explore curves more complex than ellipses, including methods for constructing them with pins and string. It wasn't just technically brilliant, it was innovative. His approach showed creativity and foresight. The paper was so advanced that the Royal Society of Edinburgh couldn't believe it had come from a child. Since James was too young to present it himself, it was read aloud by his tutor, Professor Forbes, one of the few who understood Maxwell's depth. The scientific world took notice, albeit quietly. A growing reputation. James continued to develop under the care of his father and occasional visits from scientists intrigued by the boy genius. He started reading Descartes, Newton, and Faraday. He became particularly interested in color perception and the mechanics of the human eye, a subject that would later lead him to make history. But even as his mind expanded, his social life remained limited. He was eccentric, often lost in thought, and preferred long walks in nature over social gatherings. At home, he began experimenting with polarized light, reflections, and magnetism. He built devices to measure mechanical advantage and began keeping careful notebooks, habits that would follow him into adulthood. His father encouraged his pursuits, but with some hesitation. John CLERK Maxwell had hoped his son would enter the legal profession. But after seeing the brilliance in James's early paper, he allowed the boy to pursue his passion on one condition, that he attend a proper university. The decision? University of Edinburgh. In 1847, at age 16, Maxwell enrolled at the University of Edinburgh. It was the logical first step before applying to Cambridge, the pinnacle of British science. There, he studied under renowned professors like James Forbes, geology and optics, and Philip Kelland, mathematics. His studies were intense, but he also audited courses beyond his curriculum, theology, moral philosophy, and logic. Maxwell's mind was restless, not merely technical. He began formal experimentation with color mixing, using spinning discs, painted with different hues, an early prototype of what would become the science of RGB, red, green, blue, blending. He built prisms, lenses, and rotating filters, fascinated with how the brain interprets light. At the same time, he began reading the experimental work of Michael Faraday, the self-taught genius who had discovered electromagnetic induction. Maxwell was captivated not just by the experiments, but by the mysterious fields Faraday described, invisible lines of force, curling around magnets and wires like a ghostly map of energy. For Maxwell, these were not poetic images. They were a language of the universe, waiting to be expressed in mathematics. At 17, James Clerk Maxwell had no laboratory, no institutional support, and few friends who understood him. But he had the greatest tools of all: imagination, patience, and the courage to ask the invisible questions. He had begun a journey that would soon take him to Cambridge, the temple of British mathematics. But his real journey was deeper, into the invisible world of forces, colors, molecules, and patterns. A genius had been born, and the world had only just begun to notice. Part 3. The Curious Child and the Clay Models. Genius is rarely born fully formed. It is shaped not by formal schooling alone, but by the play of the hands, the wanderings of the mind, and the silence between questions. For James Clerk Maxwell, the earliest signs of greatness appeared not in grand equations or lectures, but in the humble craft of modeling curves with clay and string. This part of his story is quiet, even overlooked, but it is here among candlelight, cardboard, mirrors, and hand-spun discs that his true genius was forged. Glenlair Estate, the laboratory of imagination. After the passing of his mother, Glenlair became more than a home. It became a laboratory of thought. His father, John Clerk Maxwell, allowed James to experiment freely. The house's library was stocked with books on mathematics, optics, and philosophy, but young James spent just as much time with tools, scissors, rulers, lenses, clay, strings, polished glass, water bowls, and mirrors. He was not content with reading theories. He had to build them. At the age of 10, James began constructing intricate models of geometrical shapes. Ellipses formed by looping string around 2 pins, conic sections carved into wood, rotating color wheels that mixed pigment before the human eye could separate them. These were not school assignments. They were expressions of a mind that needed to see ideas come alive. One relative recalled, he would spend hours alone in the drawing room, constructing models of ovals and testing how light bent through bits of broken glass. We could hear him humming to himself as he worked as though solving puzzles with joy. Geometry as a window into nature. Maxwell's obsession with curves wasn't just an artistic impulse. It was intuitive physics in embryonic form. Every shape he modeled was a simulation of nature, ellipses like planetary orbits, spirals like light waves, parabolas like the path of falling objects. To most boys, curves were drawing exercises. To Maxwell, they were laws of nature made visible. He studied Euclid with reverence, often copying diagrams by hand and extending their logic to more complex forms. Then came Apollonius, Descartes, and Newton, names he devoured with curiosity. He saw in geometry the potential to describe everything from soap bubbles to planetary motion. By the age of 12, he could explain the reflection of light on curved surfaces, the physics of lenses and how they bend images, the mechanics of color mixing using spinning discs of red, green, and blue. Though unaware, he was beginning to invent visual physics, turning the invisible into things that could be built, rotated, measured. Experiments in light and reflection. In the dim Scottish afternoons, James turned his attention to light. He filled bowls with water and studied how light bent through them. He placed candles next to spoons and mirrors to study reflected beams. He noticed how different surfaces changed the behavior of light, how ripples made it shimmer, and how angles bent it. One of his earliest experiments involved a bowl of water, a mirror submerged at an angle, and a source of sunlight through a window. He recorded how the angle of incidence equaled the angle of reflection, confirming the law of reflection with nothing more than household items. From this, he constructed diagrams of light rays, predicting paths and distortions, foreshadowing his future work in optics. The color spinners, first steps toward photography. Color, fascinated Maxwell, not just hues, but how they combined and were perceived. He began crafting color spinners, circular discs divided into colored segments, red, green, blue, etc., which, when spun quickly, appeared to blend into a single color. By adjusting the proportions of each color, Maxwell could predict and manipulate the resulting perception. These experiments were primitive but revolutionary. He wasn't just playing with color, he was testing how the eye interprets light, exploring the brain's construction of color reality, laying the groundwork for RGB color theory decades before screens existed. These spinning discs would, years later, lead directly to his invention of the first color photograph, not with chemicals or dyes, but with light, mathematics, and filters. The child philosopher. Even as he played with optics and curves, Maxwell's curiosity spilled into philosophy. His notebooks from age 13 contain deep questions. What is motion, really? Do colors exist outside the mind? What causes attraction between charged things? He was reading works on natural theology, the belief that God's design was evident in the harmony of the universe, but rather than using religion to end questions, he used it to ask more. The works of the Lord are great, sought out of all them that have pleasure therein, he once wrote in his Bible margin, underlining the call to seek truth through both faith and science. His father's gentle encouragement. Though a legal man by training, John Clerk Maxwell was open-minded and supportive. He didn't fully understand James's models, but he nurtured them. He bought books, tools, papers, lenses. He allowed James to transform parts of Glenlair into makeshift labs. He listened quietly when his son explained the paths of light and the behavior of color. It was not an academic house, but it was one of freedom, patience, and wonder. Later in life, Maxwell would say that the greatest gift his father gave him was the space to think freely. These childhood experiments, overlooked by historians and unknown to most, were the foundation of Maxwell's genius. Before the equations, before the fame, before the electromagnetic wave, there was a boy, spinning color wheels in a sunlit room, shaping ellipses out of string and pins, asking why the candle's reflection shifted with every breath. His tools were simple, his lab was a farmhouse, his power was curiosity, sharpened by patience. Part 4. The Young Mathematician of Edinburgh. When a genius is born, the world doesn't always know what to do with him. His questions seem strange, his thoughts seem too fast, and his passions too obscure. For young James Clerk Maxwell, Edinburgh would be a place of both sharpening and solitude, but it would also be the proving ground of a mathematical mind destined to reshape science. Entering Edinburgh Academy, 1841. At just 10 years old, Maxwell entered Edinburgh Academy, one of Scotland's premier schools. He was younger than most of his classmates, shorter, and certainly more awkward. He wore outdated clothes, walked with a clumsy gait, and spoke with a slow, deliberate country drawl. To many boys, he was an easy target. They called him Dafty, a cruel nickname for a boy who hummed to himself, sketched strange spirals during lunch, and asked odd questions in class. But behind the awkwardness was something none of them could match, a raw, electrifying intelligence. Obsession with Euclid. At the Academy, Maxwell discovered Euclid's Elements, and it was like opening a secret door to the architecture of the universe. He copied every proposition by hand. He reworked the proofs. He imagined new extensions of classical geometry. While his classmates wrestled with Latin and poetry, Maxwell was drawing parabolas, spirals, and ellipses, sometimes from memory. He had a unique gift, the ability to visualize abstract ideas as spatial structures. Where others saw symbols, Maxwell saw shapes, movement, relationships. The influence of Professor James Forbes. At the Academy, Maxwell came under the influence of James David Forbes, a professor of natural philosophy at the nearby University of Edinburgh. Forbes saw something exceptional in young Maxwell and began mentoring him unofficially. Forbes introduced him to more advanced mathematical ideas and encouraged him to attend public scientific lectures. It was through Forbes that Maxwell first heard of Michael Faraday, the experimental genius whose discoveries in electromagnetism had already begun to change the scientific landscape. Maxwell was fascinated. Faraday had spoken of lines of force, invisible structures that curved through space around magnets and wires. To Maxwell, this was not just science, it was a challenge, a mystery waiting to be given mathematical form. He later wrote in a letter, "Faraday's mind grasps the whole problem. He experiments and sees through things by means of lines of force. May not these lines be the very thing we require to represent the field?" The seed of electromagnetic field theory had been planted. A life of routine and rigor. James lived with his Aunt Jane Kay while attending school in Edinburgh. The Kay household was warm, deeply religious, and intellectually vibrant. Jane was a talented watercolorist, and her influence nurtured James's aesthetic sensibility, a trait rare among physicists, but central to Maxwell's future work. He walked 3 miles to school and back every day, often talking to himself, deep in thought. Neighbors and students thought him odd, but his aunt wrote lovingly of his habits. "He is never idle. If not reading, he is drawing. If not drawing, he is measuring light beams with his spinning discs." His world was ruled not by the school bell, but by curiosity, and it showed. The paper on ovals. At 14, Maxwell shocked the scientific elite by submitting a paper to the Royal Society of Edinburgh, titled "On the Description of Oval Curves and Those Having a Plurality of Foci." The paper dealt with complex geometric constructions and methods of defining curves using string and pins, and predated similar work by decades. Though too young to present it himself, his tutor, Professor Forbes, read it on his behalf. The room of scholars was stunned. Here was a teenager discussing topics that had eluded even mature mathematicians. It wasn't just brilliance, it was originality. "He does not merely understand geometry," one professor later said. "He seems to think in it." Personal solitude and quiet strength. Despite growing recognition, Maxwell remained socially withdrawn. He had few close friends and spent most of his time alone. But he was not bitter. He was serene, even joyful in his isolation. He found companionship in thought. He wandered hills, muttering formulas aloud, often sketching shapes in dirt with his cane. He didn't chase prizes or praise. His pleasure came from the elegance of truth revealed through mathematics. At home, he wrote long letters to his father full of reflections, not just on science, but on faith, life, and philosophy. Even then, Maxwell showed signs of a spiritual scientist, one who believed that understanding nature was a form of reverence. Preparing for the next leap, university. By 1847, at just 16, Maxwell had outgrown the academy. His mathematical skills were far beyond the scope of local instruction. With encouragement from Forbes, he enrolled at the University of Edinburgh. But even here, he remained humble. In lectures, he listened intently, but rarely spoke unless called upon. In labs, he built strange devices out of spare parts. At night, he copied entire chapters of Newton and Descartes by hand, annotating the margins with personal insights. His classmates considered him eccentric. His professors knew he was brilliant. At Edinburgh, he would meet the ideas that would change his life: color theory, optics, and the electromagnetic discoveries of Faraday. But more importantly, he would gain confidence. The shy boy would begin to step into his identity not as a misfit, but as a mathematical visionary. Every genius has a crucible, a time of solitude, misunderstanding, and obsession. For James Clerk Maxwell, that crucible was Edinburgh. He entered as a boy mocked for asking too many questions. He left as a mathematician who could already see the hidden structures of the universe. He hadn't yet written Maxwell's equations. He hadn't photographed the world in color, but he had found his compass, and it pointed not to fortune or fame, but to truth. Part 5. Trinity College and the Clash of Minds. If Edinburgh was where James Clerk Maxwell discovered his brilliance, Cambridge was where he would refine it, not without challenge. The halls of Trinity College, echoing with the footsteps of Newton's ghost, were filled with ambition, competition, and an elite culture unlike anything Maxwell had ever known. But for Maxwell, truth, not glory, was the goal, and in this ancient crucible of minds, he would quietly set the foundation for a revolution. Arrival at Cambridge, Oktober 1850. At the age of 19, James Clerk Maxwell arrived at Trinity College, Cambridge, the intellectual crown jewel of Britain. Here, Isaac Newton had studied centuries before. Here, mathematics was a battlefield, and only the strongest thinkers emerged as wranglers, the top mathematicians in the university. Maxwell's father was apprehensive. Cambridge was a world of privilege, formality, and competition. James was reserved, eccentric, and rural. But he carried with him something most students did not, a mind already trained in the abstract machinery of physics and form, the rigorous mathematical tripos. Maxwell's initial tutor was William Hopkins, known as the senior wrangler maker. Hopkins was famous for coaching students through the brutal tripos exam, a grueling mathematical contest that determined academic destiny. Hopkins quickly saw Maxwell's uniqueness. He wasn't the fastest at solving problems. He didn't memorize formulas like others. But his insight, his vision, was beyond anything Hopkins had encountered. Where others calculated, Maxwell conceptualized. He often solved problems geometrically or intuitively. Sometimes he found entirely new ways of understanding them. Hopkins remarked, "He is not like other students. He does not just solve problems, he sees into them." The isolation of genius. At Cambridge, Maxwell again found himself a loner. He was polite and kind, but not socially graceful. He wore unfashionable clothes, preferred walking alone at dusk, and often retreated to his room to sketch diagrams, build devices, or read theological texts. Yet those who got close to him were struck by his depth. He had a sharp wit, a gentle humor, and an almost poetic way of speaking about science. He often sang psalms in his room and found comfort in spiritual reflection. He joined the Apostles, a secret society of intellectuals that included future prime ministers and philosophers. Though religiously more orthodox than many members, Maxwell held his own in debate, often using mathematical analogies to defend his ideas about truth and unity in nature, expanding into electromagnetism and light. While his formal studies focused on the tripos, Maxwell's private reading turned increasingly toward Michael Faraday's experimental work. Faraday, who had no formal education, had discovered that magnetic fields could induce electrical current. He also introduced the concept of lines of force, invisible pathways along which magnetic and electric influences traveled. To many physicists, Faraday's lines were metaphors, but to Maxwell, they were real, and they demanded mathematical description. Here was a great divide in 19th century physics. The experimentalists like Faraday, who trusted intuition and apparatus, and the formalists who demanded equations. Maxwell wanted to be the bridge. He believed, where theory and experiment meet, truth begins to shine. In his private notebooks, he began sketching mathematical descriptions of electric and magnetic interactions. These early drafts would, years later, become the Maxwell equations, but at Cambridge, they were still embryonic. The top-ranked second wrangler. In January 1854, Maxwell sat for the tripos examination. It was an intellectual marathon lasting several days, requiring candidates to solve dozens of advanced problems. Though brilliant, Maxwell was methodical rather than quick. His answers were long, elegant, and insightful, but not always the most time-efficient. In the final results, Maxwell was named Second Wrangler, the second highest mathematical rank in all of Cambridge. It was an extraordinary honor, but many believed he was intellectually the superior of the man ranked above him. He also won the Smith's Prize, a prestigious award for original mathematical thought. His solution paper astonished judges not for its speed, but for its conceptual brilliance. Fellowship and first lectures. After graduation, Maxwell was elected to a fellowship at Trinity College. This allowed him to remain at Cambridge, conduct research, and begin teaching. He gave lectures on geometry, optics, and the philosophy of science. Students described his style as deeply thoughtful, though not always easy to follow. His ideas were often too advanced and his metaphors too abstract for common comprehension. But he was also patient, kind, and humble, more interested in expanding minds than impressing them. Marriage of faith and reason. Throughout his time at Cambridge, Maxwell remained deeply spiritual. He attended church regularly, studied biblical texts, and often wrote poems about the beauty of creation. He saw no contradiction between science and faith. To him, the laws of nature were the handwriting of God, and understanding them was a form of worship. One of his favorite biblical verses was, "Great are the works of the Lord. They are studied by all who delight in them." Psalm 111:2. He believed that mathematics was the language in which the Creator had written the universe. At Cambridge, Maxwell entered a world of great minds and emerged as one of the greatest. He did not conquer with force or flamboyance, but with clarity, humility, and vision. He came to Trinity a rural boy with a gift for geometry. He left it as a mathematician who could see the structure of space itself. His time at Cambridge was not the peak of his life. It was the foundation, the place where the equations began to form and the future of physics began to shimmer just beyond the visible. The revolution had not yet arrived, but the one who would lead it was now ready. Part 6. A Symphony of Equations. Maxwell's Four Laws. There are moments in the history of science when the universe seems to whisper its secrets into the ears of a single mind. For Isaac Newton, it was gravity and motion. For Albert Einstein, space and time. And for James Clerk Maxwell, it was the invisible symphony of electricity, magnetism, and light unified, not by machines, but by equations. The moment was quiet. There were no dramatic experiments or flashes of lightning, just chalk, a blackboard, and a man who believed the universe could be described in curves and symbols. The result would become known as Maxwell's equations, a set of 4 mathematical laws that redefined physics forever. Appointed to Marischal College, Aberdeen, 1856. After several years of study and teaching at Cambridge, Maxwell accepted a professorship at Marischal College in Aberdeen, Scotland. The environment was more provincial than Cambridge, but it offered something Maxwell deeply valued: time to think. He was 25. Most of his colleagues were older and more conservative. Yet Maxwell was given freedom to lecture, experiment, and explore new scientific frontiers. He brought with him a trunk of Faraday's experimental reports, the seeds of his coming revolution. He also brought a new personal joy: Catherine Mary Dewar, the daughter of the college's principal. They married in 1858, and Catherine became a devoted partner and caretaker of his health. She also assisted in his experiments, rare for a Victorian-era wife, but critical to Maxwell's productivity. A new language for force fields. Maxwell was fascinated by Faraday's idea of lines of force, the invisible structures surrounding magnets and electric charges. Faraday saw them as physical realities, but lacked the mathematics to describe them. Maxwell wanted to do what no one had yet done: translate Faraday's visual, intuitive ideas into mathematical law. Most physicists of the time believed that electricity and magnetism were separate forces. Maxwell believed they were aspects of one unified field, and he believed that field could be written down in symbols, in logic, in form. His method? He would treat space as filled with field vectors, quantities that had both magnitude and direction, and use differential calculus to express how those fields change in space and time. The Breakthrough, a treatise on electricity and magnetism, from 1856 to 1861, Maxwell published a series of papers laying out the foundation of his theory. But the final synthesis came in 1865 with his monumental work, A Dynamical Theory of the Electromagnetic Field. In this paper, Maxwell presented his famous set of 4 partial differential equations, now simply called Maxwell's equations. Each equation is simple in appearance, but together they describe how electric charges produce electric fields, changing magnetic fields produce electric fields, Faraday's law, changing electric fields produce magnetic fields, Maxwell's own correction, and magnetic monopoles, isolated magnetic charges, do not exist. These 4 laws captured everything known about electricity and magnetism and predicted more. Most stunningly, when he combined them, Maxwell derived an astonishing result. The equations implied the existence of waves that travel through space at the speed of light. He did the math, calculated the speed, and realized this wasn't just a coincidence. Light is an electromagnetic wave. For the first time in history, light was explained, not just observed. The universe becomes a field. To understand how revolutionary this was, consider this. Before Maxwell, physics was about particles and forces at a distance. Gravity pulled on planets. Charges attracted each other. Action happened mysteriously across empty space. Maxwell changed all of that. He introduced the concept of the field, a real physical thing that fills space and can vibrate, stretch, and ripple. Electricity and magnetism were not just interactions between particles, they were disturbances in a field, and light was a wave in that field. It was a conceptual earthquake. The idea of the field would later inspire Einstein's general relativity and quantum field theory, but it all began with Maxwell. Reaction from the scientific world. Initially, few understood the full impact of Maxwell's work. The mathematics was advanced. His style was abstract. Even some of his peers struggled to grasp the field concept. But some did understand. One physicist called it the greatest leap of the imagination in the history of physics. Another remarked, Maxwell did for electromagnetism what Newton did for mechanics. The work spread slowly, first in Britain, then in Germany. A young engineer named Heinrich Hertz would later build on Maxwell's predictions and prove the existence of radio waves exactly as Maxwell had foreseen. The equations themselves. Let us pause to look at the 4 great equations. Written in modern notation, they are Gauss's law for electricity. E equal ρ epsilon 0. Electric charges create electric fields. Gauss's law for magnetism. B. Không. No magnetic monopoles exist. Faraday's law of induction. Parit S E bia minus pia parit. A changing magnetic field creates an electric field. Ampere Maxwell law. Bete J chems B ibras mu zeran J plus mu zeran epsilon zeran zeran E. At a current or changing electric field creates a magnetic field. To physicists, these equations are poetry. They describe the invisible in perfect form, predicting the future. Maxwell's equations didn't just unify electricity and magnetism. They predicted entire new technologies: radio, microwaves, radar, X-rays, wireless communication, light as an electromagnetic phenomenon. Every radio, every cell phone, every microwave oven, they all trace their roots to Maxwell's vision. He didn't build them. He didn't patent them. He just saw what others couldn't. What Newton did for force, Maxwell did for the field. What Newton described in terms of planets, Maxwell applied to the fabric of light itself. Einstein once said, "The special theory of relativity owes its origins to Maxwell's equations of the electromagnetic field." And Richard Feynman wrote, "From a long view of the history of mankind, there is no deeper concept than the field." Maxwell didn't just write equations. He changed the language of physics. He wrote the code of the invisible and let the rest of humanity run with it. Part 7. Predicting the Invisible Birth of Radio Waves. James Clerk Maxwell never saw a radio. He never touched an antenna or tuned a signal. He lived in an age before wireless, before microphones, before the flicker of broadcast, and yet he predicted it all with equations, not equipment. This is the story of how a silent prophecy written in symbols became the foundation for the modern wireless world, and how, long after Maxwell's death, a new generation of experimenters led by a young German physicist would prove that the invisible waves Maxwell foretold were not just real, but everywhere. The mystery in the math. When Maxwell published A Dynamical Theory of the Electromagnetic Field in 1865, few fully understood it. To the average physicist, it was dense, symbolic, and abstract, but to the keen-eyed reader, something extraordinary shimmered within the math, a wave equation. By manipulating his four-field equations, Maxwell derived an expression that described a self-propagating wave, traveling at a constant speed, with electric and magnetic fields oscillating perpendicular to one another and to the direction of motion. When he plugged in the known constants, the electric permittivity, epsilon 0, and the magnetic permeability, mu 0, of free space, the result was shocking. The speed matched the speed of light. This wasn't a coincidence. It was a revelation. Maxwell realized light is an electromagnetic wave. But if light were a wave in the electromagnetic field, then there should be other kinds of waves, unseen by human eyes, longer, shorter, faster, slower. The implications were enormous. Could electricity and magnetism transmit energy across empty space? Could there be communication without wires? Could fields ripple through the vacuum like sound through air? It would take years and another man to prove it. Enter Heinrich Hertz, 1880. In the decades after Maxwell's death in 1879, physicists began to dig deeper into his theories. Among them was Heinrich Hertz, a brilliant young physicist from Germany who taught at the Karlsruhe Polytechnic School. Unlike Maxwell, who was theoretical, Hertz was experimental, practical, hands-on, and precise. He had one goal: to prove that electromagnetic waves actually exist in the real world. Many believed in Maxwell's math, but few had demonstrated its reality. Could you create these waves? Could you detect them? In 1886, Hertz set out to answer these questions. The spark gap in the receiver. Hertz designed an elegant and simple experiment. He built a device that would produce high-frequency electrical oscillations, what we now call a radio transmitter. It consisted of an induction coil to produce voltage, a spark gap, two metal balls separated by a small air gap, and a loop of wire as a receiver. When the coil discharged, it created a spark across the gap, a burst of oscillating current. According to Maxwell's equations, this oscillation should produce waves in the electromagnetic field radiating outward. Nearby, Hertz placed a second loop of wire with a small gap in it. If electromagnetic waves existed, they would travel through space and induce a spark in this second loop without wires. And they did. A tiny spark, faint but visible, jumped across the receiver gap, exactly timed with the transmitter's spark. Maxwell's waves had arrived. Measuring the invisible. Hertz didn't stop there. He began to experiment with reflecting the waves off metal sheets, like light off a mirror, refracting them through dielectric materials, measuring their wavelength and speed. He found that the waves reflected like light, refracted like light, interfered like light, traveled at the same speed as light. In every way, they behaved like light, but at a much lower frequency and longer wavelength. The electromagnetic spectrum was real. Light was just a tiny slice. Maxwell had been right. The scientific world reacted. The impact of Hertz's discovery was immense. Maxwell's theory was no longer just theoretical. It had been validated in the lab. Scientists now understood that the electromagnetic spectrum extended beyond visible light from long radio waves to microwaves, infrared, ultraviolet, X-rays, and gamma rays. The age of wireless technology was now possible. Physicists hailed Hertz, but Hertz himself remained modest. He once said, "It's of no use whatsoever. I'm not." He couldn't yet see the revolution to come, but others could. The invention of radio, Marconi and beyond. In the 1890s, an Italian inventor named Guglielmo Marconi took Hertz's discovery and ran with it. He built practical radio transmitters, created tuned circuits, and began sending wireless signals across increasing distances. In 1896, he transmitted across the English Channel. By 1901, he sent a signal across the Atlantic Ocean. What began as Maxwell's equations became telegraphy without wires, voice transmission, radio, music, news, and broadcast. By the early 20th century, radio was everywhere: ships, homes, militaries, and finally entertainment. None of it would have existed without Maxwell. The birth of the modern world. Maxwell's prediction of electromagnetic waves laid the foundation for technologies that would define the 20th and 21st centuries. Radio, radar, television, cell phones, Wi-Fi, GPS, Bluetooth, remote sensing, even quantum communication traces its ancestry to his equation. From the invisible came the connected world. It is one thing to discover something, it is another to foresee it with nothing but thought. Maxwell never saw a radio wave, never built a wireless circuit, but through the purity of mathematics, he looked into the unseen and wrote down its form. A century later, the world hums with his vision. Every call, every signal, every image sent through space. He saw what no one else did, that light and electricity and magnetism were all one, that space itself could vibrate with energy. And through this insight, Maxwell became not just a physicist, but a prophet of the invisible. Part Asham, the first color photograph, a new vision of reality, light, that ancient messenger from the stars. It carries not just shape, but color, the emotional heart of how we perceive the world. Yet for most of human history, color in images was the work of painters and dyes, not science. Until one day in 1861, when James Clerk Maxwell, already deep into equations and invisible forces, stunned the world again. He didn't just study color, he captured it. With a ribbon, a camera, and a theory of light, Maxwell produced the world's first color photograph, not by paint, but by physics. This is the story of how he turned pure science into vision, and how a mind tuned to fields and formulas became the first to freeze reality in color. Maxwell's fascination with vision and color. Before he unified electromagnetism, Maxwell had long been obsessed with light, not just its speed and waves, but its human perception. He asked questions few scientists bothered with. How does the eye distinguish colors? Are colors physical or psychological? Can all colors be made from a few primaries? These were not philosophical musings, they were scientific challenges. Maxwell believed that light and color, though personal in experience, could be studied through mathematics and experiment, and he was right. The trichromatic theory of color vision. Building on earlier work by Thomas Young and Hermann von Helmholtz, Maxwell embraced the idea that the human eye had three types of receptors, sensitive to red, green, blue. From this, he hypothesized, all perceivable colors can be produced by mixing red, green, and blue light in proper proportions. Today, this is the foundation of every screen phone, television, monitor. In the 1850s, it was radical. To test it, Maxwell built spinning color discs painted with sectors of red, green, and blue. When spun rapidly, the eye blended the colors. He recorded which combinations matched which hues, creating one of the first quantitative models of color perception. This wasn't psychology. It was optical neuroscience before its time. But Maxwell wasn't done. He wanted proof, a way to show, physically, that color itself could be reduced to science. The Royal Institution Lecture, 1861. On May 17, 1861, Maxwell delivered a lecture at the Royal Institution of Great Britain. His topic, the nature of color. But he had something spectacular planned, a live demonstration. Working with photographer Thomas Sutton, inventor of the single-lens reflex camera, Maxwell set out to create the first color photograph. But how? They followed a method Maxwell had envisioned. Photograph a multicolored object 3 times on black and white film. For each exposure, place a different color filter over the lens, red, green, and blue. Then project each developed black and white image using colored light through its corresponding filter. When overlapped, the 3 images would reconstruct the full color of the original object using only light. It was a brilliant combination of theory and practice. The subject, a tartan ribbon full of reds, greens, and blues. The world's first color photo. When Maxwell aligned the 3 filtered images using lantern projectors and the audience saw the ribbon in full color, gasps echoed through the hall. For the first time in human history, a color image had been produced without pigment, only with light, filters, and mathematics. No dyes, no paintings, just physics and perception. It was a moment that foreshadowed the entire future of imaging, RGB screens, color photography, cinema, digital media, all born in that room from Maxwell's mind. Challenges and limitations. The process was far from perfect. The photographic plates weren't sensitive to red light. The colors were faint and hard to align. The equipment was bulky, but the principle worked. Maxwell had proved that color perception is trichromatic. Light can be broken down and recombined using physics. Photography can move beyond black and white into truthful color. It was a triumph not just of science, but of vision itself. The deeper meaning of the image. To Maxwell, the photo was more than a curiosity. It was proof that the universe could be understood and recreated through its laws. He didn't just want to explain nature, he wanted to reconstruct it using mathematics as a lens. And the tartan ribbon, it was symbolic. A weave of structure and form, like the electromagnetic fields he studied, complex, harmonious, beautiful. The photo now hangs in the Cavendish Laboratory at Cambridge, immortalized as the first of its kind. Long before smartphones and pixels, before Photoshop and cinema, there was a man with a theory and a belief that the eye, the brain, and the world could all be linked by equations. Maxwell didn't just discover invisible fields, he made the unseen visible, in color, in image, in form. He didn't need a screen, he built one with science. And as you look at your phone, your monitor, your television, remember, every image of color, every pixel of light owes its origins to the man who saw it first, in numbers. Part 9. Light, Optics, and the Ether. What is light? To ancient thinkers, it was divine. To Newton, it was a stream of particles. To Huygens, a wave. But in the 19th century, light became more mysterious than ever. It seemed to behave like a wave, yet moved through space without a medium. For sound, there was air. For water waves, the sea. But what about light, which traveled across the empty void of space? Physicists call the answer luminiferous ether, an invisible substance that filled all of space, allowing light to propagate like ripples on a pond. James Clerk Maxwell was deeply drawn to this puzzle. Not only had he shown that light was an electromagnetic wave, but now he asked, what exactly is it waving in? The answer would elude him and lead, decades later, to one of the greatest scientific revolutions in history. The classical view of the ether. In Maxwell's time, the ether, or aether, was taken as fact. It was weightless, transparent, non-interacting with matter, yet somehow rigid enough to support wave propagation at 300,000 kilometers per second. Scientists couldn't detect it, but assumed it was everywhere, filling even the deepest vacuum. It was the canvas on which the universe was painted, the medium that let light cross space from the sun to Earth. Maxwell's treatment of light. Maxwell's equations had shown that changing electric fields produce magnetic fields, and together they form self-sustaining electromagnetic waves. But waves require a medium, don't they? Maxwell reasoned that if light were a wave, and he had found the wave's structure and speed, then the medium must also be implied even if invisible. He began imagining a strange type of ether, not made of atoms, but capable of transmitting stress and strain, with physical properties that mimicked mechanical elasticity, but without friction. In his own words, the velocity of the electromagnetic wave is equal to the velocity of light. We can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. Mechanical models of the ether. Maxwell, ever a geometer, began building mechanical analogies to describe electromagnetic fields and the ether. In one model, he imagined space filled with tiny spinning cells, molecular vortices, each carrying momentum and magnetic energy like miniature flywheels. He envisioned gears, rollers, even hypothetical idle wheels, transferring energy through contactless connections, metaphors for the rotation of magnetic fields and the displacement of electric fields. Though these models were not literal, they helped Maxwell visualize field behavior and build intuition. They were scaffolding for the mind until pure mathematics could stand on its own. Waves without a medium? Still, the problem remained. If the ether was real, why couldn't it be detected? Why didn't it slow the Earth? Why didn't it interfere with motion? Why didn't it drag light? No experiment could find it, Maxwell pondered deeply. Perhaps the ether was too subtle to detect, so perfectly coupled to matter it left no trace, or maybe not real at all, but just a mathematical convenience. He didn't reach a firm conclusion, but he sensed something profound. The ether, if it exists, must itself be governed by laws. And it was those laws, not the substance, that mattered most. The Michelson-Morley experiment, years after Maxwell. In 1887, 8 years after Maxwell's death, Albert Michelson and Edward Morley performed one of the most famous experiments in history. Using precision interferometers, they tried to detect the motion of the Earth through the ether, like measuring the drag of a boat in a river. But their result was null. No effect. No evidence of an ether wind. The Earth behaved as if the ether didn't exist. The physics world was shaken. Had Maxwell been wrong? Einsteins Revolution. 1905. In 1905, Albert Einstein, a 26-year-old patent clerk, published his special theory of relativity. He began with Maxwell's equations, treating them as fundamental. But instead of insisting on an ether, Einstein made a bold leap. What if the speed of light is constant, not because of a medium, but because of the structure of space and time itself? He removed the need for the ether entirely. And in doing so, he preserved Maxwell's theory and transformed physics. Einstein later said, "The theory of relativity owes its origins to Maxwell's equations. Maxwell's legacy in light. Maxwell didn't solve the ether problem, but he framed the question that would lead others to clarity. He showed that light was an electromagnetic wave, he predicted its speed, he understood its polarization and transmission, he bridged physics and human perception. He did it without seeing a single photon, decades before quantum theory, and though his mechanical models were later abandoned, the field concept he introduced became the foundation of modern physics. To Maxwell, light was never just a wave or a number. It was a window into the architecture of reality. He asked, "What is light made of? How does it move? What does it mean to see?" In doing so, he revealed not just how light behaves, but how deeply science and imagination are intertwined. He could not resolve the ether mystery, but he lit the path toward a deeper truth, one that Einstein would follow. And the light that shines on every screen today is still Maxwell's light. Part 10, Maxwell and Thermodynamics, the Demon in the Machine. Heat is life. Heat is motion. Heat is randomness. But in the 19th century, heat became something more, a window into probability, energy, and the unseen microscopic world. At the center of this transformation stood James Clerk Maxwell. Already a master of fields and light, he now turned his focus to a new question. What is heat? Really? And in doing so, he introduced a world where molecules danced, laws became statistical, and a tiny imaginary creature later called Maxwell's demon would haunt physics for over a century, the birth of thermodynamics. In Maxwell's time, the science of heat was evolving rapidly. Sadi Carnot had described ideal heat engines. Rudolf Clausius coined the term entropy, the measure of disorder. Lord Kelvin, William Thomson, connected heat with energy conservation. The second law of thermodynamics, that heat flows from hot to cold, and that disorder, entropy, always increases, was becoming the cornerstone of physics. But no one knew why this law existed. It worked. But what was happening at the microscopic level? Maxwell wanted to know. Molecules in motion. Kinetic theory of gases. Maxwell proposed that gases were made of billions of tiny, constantly moving molecules, bouncing, colliding, exchanging energy. He saw that pressure, temperature, and volume were macroscopic results of microscopic chaos. In 1860, Maxwell published a groundbreaking paper, Illustrations of the Dynamical Theory of Gases. In it, he introduced one of the most important ideas in physics, the distribution of molecular speeds in a gas, the Maxwell-Boltzmann distribution. Using statistics and probability theory, Maxwell derived a formula that predicted how many molecules in a gas move at a certain speed, how temperature affects that distribution. The result was the Maxwell-Boltzmann distribution, a bell curve-like function showing most molecules move at average speed, some are much slower, and a few are extremely fast. This was revolutionary. Before Maxwell, physics described certainties: a ball rolls this fast, a pendulum swings that far. Maxwell introduced statistical physics, the idea that laws could govern randomness. He had taken thermodynamics into the invisible world, introducing the demon. But Maxwell wasn't content. He wanted to probe deeper to question the very foundations of the second law of thermodynamics. In an 1,867 letter to his friend Peter Guthrie Tate, Maxwell proposed a thought experiment. Imagine a closed, gas-filled box divided into two compartments, A and B. Now suppose there's a tiny, intelligent being later called Maxwell's demon who can observe individual gas molecules, open and close a small door between A and B, let only fast molecules into B and slow ones into A. Over time, B becomes hotter, A becomes cooler, without doing any work or adding energy. The demon has reversed entropy. violating the second law. What was Maxwell saying? Maxwell didn't believe such a creature existed. His point was deeper. He was showing that the second law isn't absolute. It arises from probability, not necessity. If you could observe and manipulate molecules, entropy could, in principle, decrease. This wasn't just clever, it was radical. Maxwell was suggesting that information, the ability to know and act on microscopic states, had physical consequences. A century later, physicists and computer scientists would realize the demon's knowledge required energy to acquire and store. Erasing that information restores entropy. The second law survives but barely. Maxwell had anticipated information theory long before Claude Shannon or quantum computing. Backlash and praise. At the time, some physicists were unsettled. Maxwell's ideas seemed to question foundational laws. Others marveled at the depth of insight. Lord Kelvin praised Maxwell's intellectual courage. Ludwig Boltzmann would later expand on the statistical nature of entropy inspired by Maxwell and build the foundation of statistical mechanics. The power of statistical thinking. Maxwell's work opened a new way of seeing the laws of nature are not always deterministic, but arise from vast numbers of possibilities. He introduced the idea of emergent behavior, that order and thermodynamic laws emerge statistically from countless molecular collisions. This was the foundation of modern thermodynamics, statistical mechanics, and even quantum theory. Maxwell's intuition beyond numbers. Maxwell's genius lay not only in solving equations, but in asking strange questions. What if a tiny creature sorted molecules? What does heat mean at the smallest scales? Can randomness be lawful? These were the beginnings of information physics, entropy debates, and modern theories of complexity. He didn't solve every problem, but he framed them in ways that inspired generations of physicists. Maxwell's demon was not a devil of destruction, but of insight, a symbol of the boundaries between order and chaos, information and energy, mind and matter. By imagining this tiny, mischievous creature, Maxwell did something profound. He showed that even our most sacred laws may be approximations, resting on deep assumptions, and that the universe, even in its randomness, follows rules of astonishing beauty. He had once unified light and electricity, now he had unified heat and chance. And in doing so, Maxwell became not just a physicist, but a philosopher of nature. Part 11. Molecular velocity and statistical mechanics. Imagine a single puff of gas, invisible, intangible, yet filled with trillions of particles in chaotic motion. They crash, ricochet, whirl, and dart in all directions. You can't see them, but they determine everything: pressure, temperature, energy. James Clerk Maxwell saw this chaos with the mind's eye, and he knew something profound. The true laws of nature lie in the statistics of the many, not the path of the few. Now, in doing so, he created statistical mechanics, a field that would change physics forever. The limits of classical mechanics. By the mid-1800s, classical physics ruled. Newton's laws had explained gravity, motion, planetary orbits, pendulums, and even tides. Determinism reigned supreme. But gases didn't behave like planets. A balloon full of air wasn't just a collection of masses. It breathed, it expanded, it heated and cooled. And in thermodynamics, energy seemed to disappear as entropy increased. There was a mystery. Maxwell knew that gases were made of atoms and molecules, though they hadn't yet been seen. If their motion explained gas laws, then maybe probability could explain the second law of thermodynamics. A new framework, kinetic theory of gases. Maxwell built a bold new framework. Gases are composed of vast numbers of particles. Their properties, pressure, temperature, energy, arise from averages over billions of molecules. The laws of thermodynamics are statistical laws. He introduced the velocity distribution idea that in any given gas, most molecules move at average speeds, a few move very slowly, a small number race far faster than the rest. His famous Maxwellian distribution, now Maxwell-Boltzmann, was visualized as a bell-shaped curve, the precursor to Gaussian statistics. We cannot trace individual particles, but we can predict the behavior of the system as a whole. Maxwell's mathematical brilliance. In his 1,860 paper on the dynamical theory of gases, Maxwell applied the tools of integral calculus and probability theory to physical motion. He didn't just guess, he derived the average molecular speed, the most probable speed, and the root mean square speed, a crucial link to energy and temperature. He even connected molecular collisions to viscosity, thermal conductivity, and diffusion phenomena previously unexplained by classical theory. Maxwell had done the impossible. He brought precise mathematics into the statistical chaos of molecular motion. Enter Ludwig Boltzmann. Across Europe, a young Austrian physicist named Ludwig Boltzmann was reading Maxwell's work. Boltzmann recognized its brilliance and expanded it further, developing the Boltzmann equation, describing the time evolution of particle distributions, the concept of entropy as a measure of disorder, and the idea that irreversibility arises statistically from reversible laws. Maxwell and Boltzmann corresponded with mutual respect. Though they never met, their intellectual partnership defined the foundation of statistical mechanics. Maxwell once said of Boltzmann, "He is the sharpest thinker in the field of gas theory I have known." Their combined work would later support quantum theory, Brownian motion, and even the second law of thermodynamics in a probabilistic framework. A universe of probabilities. Maxwell's insights reshaped physics. He showed that certainty does not exist at the microscopic scale, that pressure and temperature are averages, not absolutes, and that laws emerge from billions of random events. This was a shift in worldview. In place of Newton's clockwork determinism, Maxwell introduced a universe of chance, patterns, and statistical inevitability. Applications and predictions. Maxwell's kinetic theory explained why gases diffuse at predictable rates, why hot gases have faster molecules, why low-mass molecules escape Earth's gravity more easily, as in hydrogen escaping the atmosphere, why specific heat varies with atomic complexity. His work guided the development of the ideal gas law in statistical terms, the understanding of molecular collisions and mean free path, the birth of molecular thermodynamics in chemistry, criticisms and vindication. At first, many scientists were skeptical. Atoms had not yet been directly observed. Some dismissed the use of statistics as guesswork. But Maxwell was patient. He knew that truth does not need approval. By the early 20th century, Einstein's explanation of Brownian motion and Perrin's experiments would prove the atomic theory of matter. Maxwell's insights were finally accepted not just as clever, but foundational. James Clerk Maxwell didn't merely describe molecules. He taught science a new way to think, not in absolutes, but in distributions, not in trajectories, but in likelihoods, not in certainties, but in beauty that emerges from chaos. He showed that order can arise from disorder, and that laws, even those of heat and motion, are written in the language of probability. Maxwell stood at the edge of the seen and the unseen and gave humanity a gift, the ability to understand the collective behavior of the invisible. And in that understanding, he became not just a scientist, but a master of nature's patterns. Part 12. The Maxwell-Boltzmann Legacy. In science, some ideas shine briefly, others fade, but a rare few become part of the bedrock, not just describing the world, but defining how we think about it. The legacy of James Clerk Maxwell and Ludwig Boltzmann is just that. Their statistical view of the universe, once radical, even heretical, is now embedded in every science that studies motion, energy, matter, and probability. Together, they created statistical mechanics and redefined the meaning of laws, order, and even reality. Atoms become real. When Maxwell and Boltzmann were working in the mid-19th century, atoms were still hypothetical. Some scientists viewed them as philosophical constructs, useful for calculations but not necessarily real. Others, like Ernst Mach, outright rejected them, insisting that science must only deal with observable quantities. But Maxwell and Boltzmann believed. They calculated the behavior of gases, temperature, and pressure based on the motion of invisible particles, and their predictions worked. Still, it would take decades and new tools to convince the skeptics. Einstein and Brownian motion. In 1905, the same miracle year in which he developed special relativity, Albert Einstein published a paper that offered proof of atoms. He explained Brownian motion, the erratic jiggling of pollen grains in water, as the result of invisible molecular collisions. Einstein used statistical mechanics, building on the foundations laid by Maxwell and Boltzmann, to predict the average displacement of particles, how motion depends on temperature and time, and even estimates for Avogadro's number. Later experiments by Jean Perrin confirmed Einstein's predictions and, by extension, confirmed the reality of atoms and molecules. Maxwell had been right all along. Entropy, probability, and the arrow of time. Perhaps the most powerful and controversial legacy of Maxwell and Boltzmann was the idea that entropy is not a rigid rule, but a statistical tendency. According to their work, systems naturally evolve from less probable to more probable states. That is, from order to disorder. Entropy is a measure of the number of microscopic configurations that correspond to a given macroscopic state. This concept led Boltzmann to his famous equation, SK, glug, where S is entropy, K is Boltzmann's constant, W is the number of microscopic arrangement. This equation is now engraved on Boltzmann's tombstone in Vienna, a tribute to the statistical universe he helped reveal. But this also raised new questions. If entropy is probabilistic, can it sometimes decrease? Can fluctuations momentarily reverse time's arrow? What does that mean for the future of the universe? Maxwell's demon re-entered the debate as a symbol of how information and probability intertwine. Foundations of quantum and statistical physics, the statistical revolution launched by Maxwell and Boltzmann would ripple through the 20th century. Niels Bohr, Max Planck, and Werner Heisenberg embraced the probabilistic view of particles in quantum mechanics. The partition function central to statistical mechanics became a vital tool in both classical and quantum thermodynamics. The Boltzmann distribution became the foundation for studying systems in thermal equilibrium. Even modern cosmology uses statistical mechanics to model the early universe, the cosmic microwave background, the formation of galaxies. Statistical thinking was no longer just about gases. It had become a universal framework, chemistry, biology, and beyond. The Maxwell-Boltzmann legacy extends well beyond physics. In chemistry, reaction rates, diffusion, and equilibrium constants depend on statistical models. Kinetic theory explains why some molecules react and others don't. In biology, protein folding, enzyme activity, and cell thermodynamics are modeled using entropy and probabilities. The behavior of populations, from gene drift to epidemic spread, draws from Maxwellian concepts. In information theory, Claude Shannon borrowed entropy directly from Boltzmann's work to define information entropy, the heart of digital communication. Every data transmission, every image, every compressed file owes something to statistical physics. The philosophical shift, Maxwell and Boltzmann didn't just change equations, they changed how scientists think. No longer could laws be viewed as absolute certainties. Instead, they were emergent patterns from chaos averages over possibilities. Nature was still lawful, but now it whispered in probabilities, not commands. This influenced Popper's philosophy of science, Bayesian statistics, and the rise of complex systems science. Today, economists, ecologists, and even sociologists use statistical ensembles and entropy to describe dynamic, uncertain worlds. Maxwell and Boltzmann, two minds, one vision. Maxwell was the gentleman soft-spoken, mathematically elegant, full of metaphor and modesty. Boltzmann was the fighter passionate, combative, deeply emotional, often misunderstood. Though their lives were different, their work interlocked like gears in a cosmic engine. One framed the structure, the other expanded and defended it. Together, they created a new language for science. The legacy of Maxwell and Boltzmann is not carved in marble, but written into the motion of every molecule, the code of every algorithm, the warmth of every sunbeam. They showed us that even in chaos there is clarity, that from disorder comes law, that nature's randomness is not wild but mathematically beautiful. They transformed uncertainty into insight, chance into law, and invisible collisions into universal equations. And in doing so, they gave us more than just formulas. They gave us a way to understand the dance of existence itself. Part 13, Faith and Science, the Mind of a Philosopher. James Clerk Maxwell is remembered as a physicist, a mathematician, a pioneer of electromagnetism and molecular theory. But behind the equations, behind the spinning color wheels and symmetrical fields, was a deeply spiritual man. Not a zealot, not dogmatic, but a scientist who believed that truth was not the enemy of faith, that the laws of nature were, in fact, echoes of something eternal. This is the story of Maxwell's inner life. A man who prayed in silence, read Scripture in solitude, and saw the beauty of God in every curve of nature. Early influences and family devotion. Maxwell's childhood was immersed in Scottish Presbyterianism, a faith known for its seriousness, discipline, and deep intellectualism. His mother, Frances Kay, taught him the Psalms and Proverbs by heart. Even after her death, he remembered her soft voice, reciting lines like, "The works of the Lord are great, sought out of all them that have pleasure therein." Psalm 111:2. This verse became a personal compass. To Maxwell, studying the universe was not separate from worship, it was worship. The gentleman believer, Maxwell was not showy in his faith. He rarely argued theology in public, never sought attention for his beliefs, and avoided sectarian debates. But those who knew him well, family, colleagues, students, all described him as prayerful, thoughtful, humble, and unwavering in his sense of moral responsibility. He read Scripture daily. He wrote theological reflections in his private journals, and he maintained correspondence with clergy and scientists alike, discussing not just what the world was, but why it existed. His philosophy of creation. Maxwell did not see God in gaps as a mere explanation for the unknown. Instead, he believed that the laws of physics revealed something deeper. Order, not chaos. Consistency, not randomness. Beauty, not accident. The only desire which I can have is like David, to serve my own generation by the will of God, and then fall asleep. Maxwell's science was not because he doubted faith, but because he wanted to understand God's craftsmanship. To him, every symmetry, every pattern, every field equation was a glimpse of something transcendent. Faith in the face of uncertainty. Maxwell's era was one of intense religious and scientific tension. Darwin's Origin of Species had shaken traditional theology. Materialism was rising. Many scientists became agnostics or atheists. But Maxwell did not retreat, nor did he reject science. Instead, he stood in the middle, embracing both rigorous thought and humble faith. He accepted mystery where necessary, but always sought coherence. Science is competent to describe the order of things. It cannot account for the origin of that order. In other words, science tells us how, but not why. His view of the soul and morality, Maxwell believed deeply in the immortality of the soul and the moral law written into the human heart. He once wrote, "The mind of man is not merely a register of facts, but is endowed with insight, choice, and the capacity to recognize law." He believed that humans were moral agents, that free will was real, that conscience was not an illusion, but a gift from the Creator. His morality was simple: live truthfully, seek wisdom, serve others, do no harm to truth or to your fellow man. The Sabbath scientist. On Sundays, Maxwell did not lecture. He read theology, walked in nature, and reflected. He once said, "The Sabbath is a time not for idleness, but for renewing the soul." He often sang hymns and recited psalms aloud while walking the countryside. It was said that he could recite the entire book of Psalms from memory. Correspondence with clergy and thinkers. Maxwell maintained letters with clergy and scientists who wrestled with questions of miracles, free will, the soul, the compatibility of faith and evolution. In a letter to a doubting colleague, Maxwell wrote, "I think men of science, as well as other men, need to learn from Christ. And I think Christians whose minds are scientific are bound to study science, that their view of the glory of God may be as extensive as their being is capable." And he did not believe in compartmentalizing knowledge. To Maxwell, theology, ethics, and science were all rays of light from the same source. Facing death with grace. In 1879, Maxwell was diagnosed with abdominal cancer, the same illness that had taken his mother. Though he endured months of pain, he remained serene. He continued to write, teach, and pray. His final days were spent at home, surrounded by Catherine and close friends. When asked if he feared death, he said, "I have been thinking how very gently I have always been dealt with." His final words to a visitor, "It is a very different thing from what it seems to be to the bystanders." He died on the 5th of November, 1879, at the age of 48 content, humble, at peace. Maxwell's equations changed the world, but his character grounded them in something deeper. He sought truth, but not pride. He worshipped with mathematics, but lived with compassion. He walked between galaxies and Scripture, never fearing the space between. He showed the world that a scientist could believe, that faith need not be blind, that to understand creation was to draw nearer to the Creator. He left no sermons, no pulpits, only patterns, light, logic, and love. And in every corner of the universe, where electricity flows, light travels, and order reigns, you can feel the quiet heartbeat of Maxwell's faith. Part 14. The Cavendish Laboratory and the Next Generation. James Clerk Maxwell changed the world with his mind. But before his untimely death, he also planted something else. A place, a sanctuary for precision, a home for curiosity, a temple of measurement. That place was the Cavendish Laboratory at Cambridge. More than just bricks and mortar, it was Maxwell's final and most powerful gift to science, a place where thought met action and where the greatest discoveries of the 20th century would begin. Cambridge reorganizes science. By the late 1860s, Cambridge University was facing a scientific problem. For centuries, its strength had been mathematics and philosophy, but the modern world was moving fast toward experimentation, engineering, and applied science. They needed a physical laboratory, a space to train the next generation of scientists, not just in theory, but in hands-on observation. The wealthy Cavendish family, descendants of the great Henry Cavendish, offered a generous endowment. The university approved a plan, but they needed a director. There was only one choice. Maxwell appointed as first Cavendish professor, 1871. In 1871, Maxwell was appointed the first professor of experimental physics at Cambridge and tasked with designing and founding the Cavendish Laboratory. He accepted with humility and vision. This was more than a job. It was a chance to institutionalize the spirit of discovery, to build not just walls and rooms, but a culture of precision, honesty, and curiosity. Maxwell helped plan the architecture, selected the instruments, and even wrote the first laboratory manual, setting the tone for how experiments should be conducted and recorded. Null methods and the philosophy of measurement. Maxwell believed that experimentation was not just about tools, it was about rigor. He emphasized accuracy over drama, systematic procedure over improvisation, skepticism over spectacle. One of his core principles was the use of null methods. The most precise way to measure a difference is to eliminate it to measure when nothing happens. This meant balance scales rather than estimating weights, bridge circuits rather than voltmeters, methods that detected equality, not magnitude. This approach allowed astonishing accuracy and became the gold standard for physics labs across the world. Building a generation of experimentalists, Maxwell's students were not just pupils, they were apprentices in the craft of truth. He trained them in building apparatus from scratch, calibrating instruments with obsessive care, logging every result, including anomalies. He discouraged speculation unsupported by data, but he encouraged creative design, asking students to modify and improve existing tools, learn to observe with suspicion, and to think with humility. Among his earliest students were minds who would go on to discover new elements, measure constants of nature, build the foundations of quantum mechanics and atomic theory. The Cavendish was not a factory, it was a forge. After Maxwell, the lab lives on. Maxwell died just 8 years after becoming Cavendish professor, but the laboratory he created would live on and change the course of human history. Future Cavendish professors included Lord Rayleigh, who discovered argon and refined Maxwell's theories, J.J. Thomson, who in 1897 discovered the electron, the first subatomic particle, Ernest Rutherford, who uncovered the structure of the atom and performed the gold foil experiment, James Chadwick, who discovered the neutron, and later Francis Crick and James Watson, who in the 1950s revealed the structure of DNA right inside the Cavendish walls. All of this traced back to Maxwell's vision. He had built the stage. Others performed the drama. The culture Maxwell created, Maxwell's influence went beyond equations. He instilled values, integrity in data, humility in discovery, joy in precision. He rejected arrogance. He laughed at scientific egos. He once said, "In science, we are all apprentices of nature." His lab was quiet, methodical, and serious, yet full of wonder. It was a place where truth wasn't discovered so much as it was revealed through patience. That ethos endured for generations. Maxwell's final manual. One of Maxwell's last written works was the Cavendish Laboratory Handbook, a guide to instruments, methods, and principles for experimental students. In it, he laid out not just instructions, but a philosophy that experiments must be repeatable, that error must be acknowledged and minimized, that instruments must be understood, not merely used. Even today, physicists marvel at the clarity and wisdom of Maxwell's handbook. It is part physics, part ethics, part poetry. Most scientists leave behind papers, theories, and data. Maxwell left all of that and a living laboratory. He built a place where curiosity became discipline, where ideas were tested against nature, and where generations of minds were shaped. In every breakthrough from the Cavendish, from electrons to neutrons to genomes, you can hear the echo of Maxwell's voice. Let the data speak, let nature answer, and let the joy of precision be your guide. Part 15, A Final Journey, Illness and Death. For most of his life, James Clerk Maxwell walked in the company of light, revealing the invisible, building laboratories of wonder, writing equations that would echo through time. But in the autumn of his years, darkness approached, slowly, silently, and yet Maxwell met it not with fear or denial, but with the same spirit that had guided all his science: grace, clarity, humility, and awe. A subtle decline. In 1877, while serving as Cavendish professor at Cambridge, Maxwell began to feel unusual fatigue. He was only 46, still lecturing, writing, and overseeing experiments, but there were signs: pain in the abdomen, difficulty eating, gradual weight loss. He dismissed it at first, but the discomfort returned persistent and unrelenting. He had no idea that the illness he now faced was the same one that had taken his mother decades earlier. Diagnosis: abdominal cancer. By 1878, the pain had become impossible to ignore. Doctors examined him and delivered the devastating news: advanced abdominal cancer. It was likely pancreatic or stomach cancer, poorly understood at the time, and with no known cure. Maxwell was 47 years old. The prognosis was grim, but his response was quiet, measured, composed. He confided in close friends, wrote fewer letters, and began to prepare mentally, spiritually, and scientifically. A life still in motion. Despite increasing pain, Maxwell continued his duties at Cambridge. He revised papers, edited his students' work, gave lectures when he could, worked on finishing the Cavendish Laboratory Handbook. Visitors noted that his voice had softened, his frame had thinned, but his mind was as sharp as ever. He still smiled, still made jokes, still wandered the lab late into the evening to check on equipment. To the very end, Maxwell was present, engaged in the world he had helped define. Returned to Glenlair. By mid-1879, Maxwell could no longer teach. He left Cambridge and returned home to Glenlair House in the Scottish countryside, the place where he had first played with string and light, where he had imagined the universe in curves and colors. He was now back among the moors, the mist, and the memories. His beloved wife, Catherine, cared for him with quiet devotion. They read Scripture together, walked in the garden when his strength allowed, watched the changing sky as they had done for years, facing the end. As his condition worsened, friends visited, often hoping to comfort him, but it was Maxwell who brought them peace. To one visitor he said, "It is a very different thing from what it seems to the bystanders." He spoke of death not with dread, but as a transition, a passage to something deeper, greater, more radiant. He did not ask, "Why me?" He asked, "What next?" The final hours. In the last days of October 1879, Maxwell's condition deteriorated quickly. He slipped in and out of consciousness. At times he quoted psalms from memory. At others he simply gazed out the window as if already seeing something beyond it. On the morning of the 5th of November, surrounded by Catherine and a few close friends, James Clerk Maxwell passed away peacefully. He was 48 years old. The world lost one of its most luminous minds. Aftermath and burial. Maxwell's body was laid to rest in the small churchyard of Parton, not far from Glenlair. The headstone is modest. There are no grand statues, no sprawling inscriptions, just a name, a date, and a life that rewrote the very structure of reality. Tributes and reflections. The scientific world was shaken. Tributes poured in from across Europe and beyond. Lord Kelvin, who had sometimes disagreed with Maxwell, wrote, "From a long view of the history of mankind, seen from, say, 10,000 years hence, there can be no doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electromagnetism." His obituary in Nature read not like a death notice, but like the farewell of a hero. Friends remembered not just his genius, but his warmth, humility, and humor. A legacy in motion. Though Maxwell died young, his work did not. Within a decade, Hertz confirmed the existence of electromagnetic waves. Marconi would use those waves to create radio. Einstein would build relativity atop Maxwell's laws. Quantum electrodynamics would evolve from his field equation. Even today, Maxwell's insights form the infrastructure of civilization powering light, electricity, communication, computation. He is everywhere, yet so few know his name. Maxwell's death was not a defeat. It was a passing of the torch from one century to the next, from the age of steam to the age of electricity and light. He had given humanity the equations of energy, the laws of light, the rhythm of molecules, and the ethics of a truth-seeking mind. And he had done it all with grace, with faith, and with quiet brilliance. He died as he lived, seeking patterns, honoring beauty, trusting in the harmony of creation. And though he rests in the Scottish earth, his light still moves at 299,792,458 meters per second, carrying his name across the stars. Part 16. Maxwell's influence on Einstein, Planck, and modern physics. James Clerk Maxwell died in 1879, quiet, serene, almost unknown to the general public. But from the blackboards of Cambridge to the laboratories of Berlin, his equations lived on, not as relics, but as prophecies. In a single set of 4 elegant formulas, he had described a field, something that pulsed, rippled, and traveled through space at the speed of light. Decades later, young minds would pick up those equations and see more than Maxwell himself had dreamed. What followed was not just an age of discovery, it was a redefinition of space, time, light, and matter. Einstein's first inspiration, the speed of light. Albert Einstein was born in 1879, the year Maxwell died. By the time he was a teenager, Einstein was reading Maxwell's electromagnetic theory with awe. But there was a paradox. According to Maxwell's equations, the speed of light was constant, regardless of the observer's motion. That defied common sense and Newtonian mechanics. Einstein later recalled, "When I was 16, I asked myself, what would it be like to ride alongside a beam of light?" This thought experiment, sparked by Maxwell's equations, became the seed of special relativity. Special relativity, 1905. In 1905, Einstein published his theory of special relativity, based on 2 postulates. The laws of physics are the same in all inertial frames. The speed of light in a vacuum is constant, regardless of the motion of the source or observer. This second postulate came directly from Maxwell's equations. Einstein realized Maxwell's equations require the speed of light to be fixed, therefore space and time must adjust, not the speed. He showed that time dilates, length contracts, mass and energy are equivalent. Maxwell's field equations weren't just about electromagnetism, they were the key to space-time itself. Einstein on Maxwell. Einstein held Maxwell in the highest regard. In 1931, on the centenary of Maxwell's birth, he wrote, "The special theory of relativity owes its origins to Maxwell's equations of the electromagnetic field." And elsewhere, one scientific epoch ended and another began with James Clerk Maxwell. For Einstein, Newton had ruled the physical world, but Maxwell had revealed the geometry of fields, which would soon become the language of relativity and gravitation. Planck and the birth of quantum theory. Meanwhile, in Germany, another physicist was studying Maxwell's equations in a different context, blackbody radiation. Maxwell's electromagnetic theory predicted how energy should be distributed in heated objects, but experiments revealed an ultraviolet catastrophe. The theory broke down at high frequencies. In 1900, Max Planck made a disparity adjustment. He proposed that energy is quantized, emitted in discrete packets, or quanta. This tiny correction, meant to save Maxwell's classical framework, accidentally launched quantum theory. Planck called his solution an act of desperation, but it changed the world. Scene: quantum electrodynamics and Maxwell's equations. As quantum physics matured, scientists tried to merge it with electromagnetism. The result was quantum electrodynamics, QED, the most precise physical theory ever constructed. QED preserved Maxwell's field equations, but described light as quantized packets, photon, and modeled interactions between matter and fields using probability amplitudes. The fundamental beauty of Maxwell's work was not discarded. It was refined, expanded, quantized. Even Feynman diagrams, used to calculate particle interactions, describe electromagnetic processes that follow Maxwell's original laws, but with a quantum twist, unified field theory, and modern physics. Einstein spent the last decades of his life trying to create a unified field theory, a single framework to combine gravity from general relativity, electromagnetism from Maxwell, and eventually the quantum world. Though he never succeeded, the attempt reflected the truth. Maxwell's vision of unity in physical forces had planted the idea that all forces might be connected. Today, physicists continue the quest through string theory, loop quantum gravity, grand unified theories. Every one of them owes a debt to Maxwell. Maxwell in modern technology. Even outside of theory, Maxwell's influence pervades modern life. His equations govern electromagnetic waves, radio, television, Wi-Fi, Bluetooth, cellular network. They explain light propagation through fiber optics. They're the foundation of circuit design, radar, GPS, remote sensing. Every simulation of electric fields, magnetic resonance, or satellite communication starts with Maxwell. The math on your screen, in your phone, in your spacecraft, it traces back to his chalkboard. Maxwell and the language of the universe. What Newton did for force and motion, Maxwell did for fields and light. But Maxwell did something more profound. He introduced mathematical symmetry as the deepest language of physics. His equations are elegant, compact, universal. They form a set of partial differential equations that are Lorentz invariant, gauge invariant, and relativistically consistent. They are beautiful not just to physicists, but to mathematicians, philosophers, even artists. James Clerk Maxwell never lived to see. The electron discovered, the quantum born, relativity rise, or photon defined. Yet his equations contained them all hidden in form, awaiting interpretation. He was the last classical physicist, and yet the first truly modern one. His work was not a conclusion, it was a beginning. In every new particle found, in every wave detected across space, in every transformation of energy, Maxwell speaks. He whispers in electric pulses, sings in starlight, echoes in fiber, and hums in the circuits of our age. And in the minds of Einstein, Planck, Feynman, and beyond, Maxwell lives. Part 17. Legacy in the Digital Age. In the digital age, the world runs on signals, light, and information. Yet behind the invisible waves that stream through our homes, behind the smartphones in our pockets, and even the images captured from galaxies light years away, one man's work quietly sustains it all. His name was James Clerk Maxwell. His voice is everywhere, though we do not hear it. His hands built our world, though we do not see them. This is Maxwell in the digital age, a presence woven into every byte, beam, and broadcast. Communication, the wireless world. Maxwell's prediction of electromagnetic waves laid the foundation for all wireless communication. In radio, Hertz detected the waves Maxwell predicted. Marconi used them to send messages across the Atlantic. In television, visual and audio signals became electromagnetic modulations. In satellites, signals bounced through space, precisely timed using Maxwell's math. In mobile phones, each call is encoded, transmitted, and received using field equations he first derived. From 3G to 6G, from Wi-Fi to GPS, every bit of wireless communication obeys Maxwell's laws. Every phone call you make is, in essence, a tribute to Maxwell. Imaging from the first color photo to pixels. Maxwell was the first person to produce a color photograph using red, green, and blue light long before digital screens existed. Today, every screen from smartphones to TVs to VR headsets uses the RGB color model Maxwell helped pioneer. Digital cameras and sensors rely on photon detection following the principles of electromagnetic energy Maxwell quantified. Medical imaging, MRI, Connecticut, ultrasound use Maxwell's equations to map energy fields inside the human body. In every pixel you see, Maxwell's color theory is working behind the scenes. Engineering, electricity, and circuitry. Electrical engineering as we know it is Maxwellian at its core. Circuit analysis depends on electric and magnetic field. Power grids operate based on alternating current behaviors predicted by Maxwell's models. Transformers, motors, and generators, first theorized by Faraday, were fully explained using Maxwell's framework. Engineers simulate field strengths, signal propagation, and interference using finite element models that solve Maxwell's differential equations numerically. Every computer chip, every PCB, every electric car follows the geometry of invisible fields that Maxwell made visible. Maxwell in computation and simulation. Modern physics and engineering rely not just on experiments, but on simulations. Maxwell's equations are so fundamental that they're embedded in computational physics engines, used in video game rendering for realistic lighting, employed in weather prediction models, radar and remote sensing, crucial in aerospace design, antenna arrays, stealth technology. Software like COMSOL, ANSYS, and MATLAB includes solvers for electromagnetic field problems based on Maxwell's equations. Every simulation of light, heat, or force begins with his language, digital security, and electromagnetic shielding. From secure data centers to aircraft avionics, electromagnetic compatibility is mission critical. Maxwell's theory predicts how signals leak, reflect, or interfere. Engineers use Faraday cages designed using his principles to shield sensitive equipment. In cybersecurity, electromagnetic side-channel attacks are countered with techniques derived from Maxwellian field control. Even stealth aircraft are shaped based on how they deflect radar waves understood via Maxwell's model. Space exploration and astronomy. Maxwell once studied Saturn's rings and concluded they were made of individual particles, not solid bands. His theory was confirmed by spacecraft over a century later, but his influence goes much further. The James Webb Space Telescope receives light that traveled through Maxwellian space. Antennas aboard Voyager and deep space probes rely on radio waves to send signals engineered using Maxwell's principles. Plasma physics in the solar wind, auroras, and solar flares obey the electromagnetic field theory he developed. The search for alien life, the mapping of cosmic microwave background radiation, the exploration of exoplanets all ride on light, fields, and signals Maxwell described. AI, machine learning, and quantum tech. Even cutting-edge technology owes him a debt. Optical fibers transmit data using total internal reflection, guided by Maxwell's wave equations. Quantum computing systems must be designed to shield or exploit electromagnetic fields at the nanoscale. Neural networks trained on light-based input, like vision, still process data encoded through Maxwell's mathematics. If AI is the brain of the future, Maxwell is its nervous system. Maxwell as a standard bearer. Maxwell's equations are now carved into stone at MIT and Cambridge, engraved on metals, taught in every undergraduate physics program on Earth. They are as fundamental as the alphabet of science. His name lives in the Maxwell distribution, Maxwell's demon, the Maxwell-Boltzmann statistics, and even the unit of magnetic flux, the Maxwell in CGS units. But his deeper legacy is a way of thinking. That nature is mathematical, that truth can be beautiful, that the invisible world can be mapped with elegance. The digital age is not just the age of silicon or code. It is the age of fields. And the first person to write down those fields clearly, completely, with courage and care was James Clerk Maxwell. He never saw a computer, never heard a radio, never watched a video stream through space, but he made all of them possible. In every signal received, in every image captured, in every calculation performed, there is a silent, invisible tribute to the man who saw the structure of the unseen. In the age of AI, satellites, and quantum entanglement, we are still, in every sense, living in Maxwell's world. Part 18, Epilogue, The Man Who Saw the Invisible. In a quiet graveyard in Parton, Scotland, beneath a simple stone, rests a man who changed the world. There is no towering monument, no cathedral built in his name, and yet the reach of his mind stretches from the heart of atoms to the edge of galaxies. His name, James Clerk Maxwell. He was not a celebrity, not a warrior, not a politician, but he was a man who, through thought alone, unlocked secrets that had been hidden since the dawn of creation. He did not build the tools of the modern world. He wrote the instructions. The whole man, a harmonious life. Maxwell was not just a scientist, nor merely a mathematician. He was a poet, a philosopher, a devout Christian, a quiet reformer of scientific thinking. He lived not for glory or titles, but for understanding. He combined the cold elegance of mathematics with the warmth of moral reflection, the rigors of precision with the softness of personal humility, the grandeur of theory with the joy of experimental tinkering. To Maxwell, the world was not just measurable, it was beautiful. Patterns, fields, and unity. He saw something others had missed, that light, magnetism, and electricity were not separate things, but aspects of a deeper unity. This unity wasn't metaphorical, it was mathematical, elegant, precise. His 4 equations, simple yet complete, described a reality more profound than anyone had imagined. He gave us the field, the wave, the symmetry, the unseen structure that supports everything. And in doing so, Maxwell did more than describe nature. He helped humanity see that the universe itself is intelligible. The last of the classical, the first of the modern. Maxwell stands at the crossroads of scientific history. He was the last classical physicist still grounded in geometry, elegance, and harmony, and the first modern physicist foreshadowing Einstein, Planck, Schrödinger, and Heisenberg. His thinking was not bound by time. It belonged to a future yet unwritten. When Einstein began his journey into the nature of space and time, it was Maxwell's equations that lit the path. When Planck cracked the quantum world, it was to solve a problem in Maxwell's theory. When Feynman mapped out particle interactions, he was painting with Maxwell's brush, but on a quantum canvas. Quiet genius. Maxwell never sought fame. He preferred walking the moors with his wife, reciting psalms, sketching curves in the sand, solving problems in solitude. He was modest in speech, kind in conversation, and generous with credit. He published slowly. He thought deeply. He praised others freely. And yet, when the time came to measure his place in history, his peers knew the truth. Lord Kelvin said, "Maxwell is undoubtedly the greatest mathematical physicist the world has seen since Newton." Einstein said, "The work of Maxwell changed the world forever." A message for the future. Maxwell's legacy is not just in his equations. It is in how he thought, how he lived, and what he valued. His life teaches us that beauty and truth are not in conflict, that humility and genius can coexist, that science can be a form of worship, that quiet work can echo for centuries. He invites us not just to know, but to see, to look at the world and ask, what invisible harmony lies beneath this? He believed the answers were there not always in plain sight, but waiting for those who would look patiently, faithfully, mathematically. In the end, light, in the final year of his life, weakened by illness, Maxwell still gazed at light. He understood that light was more than brightness. It was the vibration of the void, the language of the stars, the messenger of the divine. And in that light he had seen color, motion, fields, order. He had seen the unseeable. And in doing so, he showed humanity that the invisible is not unknowable, only unlooked for. Today, we live in Maxwell's universe. His equations govern the screens you read on. His distributions shape the air you breathe. His waves connect your devices across continents. Every moment of modern life is a quiet acknowledgement of a man whose name too few remember, but whose mind remembers us all in the very structure of reality. To say Maxwell was a genius is too small. He was a seer of the unseen, a poet of precision, a cartographer of the invisible, and in the hum of electricity, in the shimmer of light, in the warmth of a signal traveling through space, James Clerk Maxwell still speaks.